All right, well, it's good to see you all here, all couple dozen of us. I appreciate you making it over to this talk. So today I'm going to talk about my work on the intermediate infrared wavelength range. Many of the people in this audience are probably familiar with the abundant contributions of visible near-infrared and mid-infrared remote sensing to the detection of minerals across the surface of the moon and other planetary bodies. Many of you are probably also familiar with the fact that one of the big variables that remains largely unknown across the moon and elsewhere is the chemical composition of minerals that exhibit solid solution chemistry, such as olivine, pyroxene, etc. And this in turn leaves much unknown about the evolution of planetary crusts. And so for those of you who are familiar with infrared remote sensing, you probably typically think about this wavelength range over here, the visible near infrared, or this wavelength range, and then further out, the mid infrared and far infrared. Today, I'm going to talk about this wavelength range in between, which I've referred to in previous presentations as the crossover range, but henceforth I refer to as the intermediate infrared. So a couple of years ago, we published a paper on the intermediate infrared spectroscopy of olivine. Now, here we see spectra from in the 4 to 8 micron range of synthetic olivine, first described by Darby Dyer. And most notably, we see strong spectral bands at 5.6 and 6 microns. And as we go from Mg-rich at the top to Fe-rich at the bottom, the positions of these two spectral bands shift systematically to longer wavelength range, to longer wavelengths. And these systematic trends in band position are consistent across both synthetic samples and a large range of natural terrestrial pure olivine samples. Now, the next question that we posed for ourselves was what can we do with pyroxenes, which have remained for a long time a significant challenge for the visible near infrared. So first, I examined calcium-free pyroxenes shown here, ranging from enstatite to ferrocylite, and we focused in particular on a well-defined band at it says 5.1, it should be 5.2 microns, and this band at approximately 5.2 microns likewise shifted systematically from shorter to longer wavelengths with an increase in iron content. So then the next question was, what happens in the high calcium pyroxenes, which is a particular challenge because of the confounding influences of variations in Mg-Fe content and calcium content. What we see is that there are two well-defined bands at 5.1 and 5.3 microns. And the positions of these bands shift only as a function of Mg number and shift likewise to longer wavelengths with increasing Fe. And that the only change that occurs as a function of calcium content is the relative strength of the 5.1 and 5.3 micron bands. So when we look at all these results in their totality across the synthetic and natural pure olivine and pyroxenes, what we see are several well-defined trends in the relationship between the minimum position of these bands and the Mg number of these pure mineral samples for both for high calcium pyroxenes in gray, for low calcium pyroxenes in blue, and olivines in green. And these relationships enable us to determine Mg number within plus or minus 10 mole percent, or plus or minus 20 mole percent in the case of high calcium pyroxene. So now the question is, how do we apply this to the moon? So the first step that we took was to investigate these trends in particulate mineral mixtures. We looked at mixtures of olivine, pyroxene, and anorthite. I've shown only the results for the olivine and anorthite mixtures here. And what we find when we look at these series of mixtures of olivine and green on top and anorthite and magenta on the bottom is that we're able to determine olivine Mg number within plus or minus 10 mole percent at abundances as greater than 20 weight percent olivine. And this trend is broadly true for olivine pyroxene plagioclase mixtures, both in reflectance and emissivity data. And what this implies is that our results will be robust for not only pure minerals or, let's say dunites and peroxides, but also for materials such as troctolites. Now, the outstanding question is, can Mg number of olivine and pyroxene be quantitatively determined in natural rock samples, not just in particulate mixtures? So the next part of the study, the present work, has involved investigations of olivine and pyroxene-rich rock samples from the Moon, Mars, and meteorites. And what we focus on in particular is comparing the positions of the minima of the Mg number diagnostic bands between samples that have both whole rock samples and mineral separates. And what we have found when we look at all these samples is that there's a strong agreement in the positions of the Mg diagnostic bands between the whole rock samples and the mineral separates. So let's look at this spectral plot on the left. What we have are low calcium pyroxene dominated samples that vary in the abundance of pyroxene from 97 weight percent to as low as 52 weight percent. And what we see between the mineral separates and dashed lines and the whole rock samples and solid lines is a general resemblance in the shape of the spectra. This is broadly true for the olivines and for the high calcium pyroxenes as well, with a couple of interesting cases where we have both olivine and pyroxene detectable within an individual sample. So let's return to a plot that we looked at a few slides ago, where we look at the relationships between the Mg number and the position of the band minima. And these green, blue, and gray dots indicate pure samples, synthetics or natural terrestrial mineral separates. Now let's superimpose the samples that sample compilation that we just looked at. All the samples, these new samples are in orange. The dark orange are whole rock samples, whole rock particulate samples, and the light orange indicate the mineral separates. And what's most significant about this graph is that we see a broad degree of agreement between the trends that we established earlier and samples that cover a wide range of rock types that we would expect to encounter on the Moon. So if you are interested in the implications of this work for the chemical characterization of minerals on the lunar surface, and also in the direct detection of H2O, please see my poster just outside on the Lunar Intermediate Infrared Imaging Spectrometer, or LIRIS. And I'd be happy to talk to you more about this concept, which we're interested in having on Endurance and other missions as well. So with that, I'd like to thank sponsors of this work, and I'd like to thank you for your time today.
All right, fantastic. Thanks for the talk. Another really good talk, and talking about different wavelength range. Don't leave yet. We might have some questions for you in the room or online. Any in the room? And I'll have one if there are none online. Maybe adjusted already.
Can I ask a question?
None online?
Oh, I think Lindsay had a question.
Wants to ask one online.
Sure, go ahead.
Yeah, thank you. So this is Lin Jison from University of Hawaii. So I developed a magnesium number estimation model using Hupke's theory, but I'm using the near infrared. I'm wondering, are you willing to compare your result with mine? So.
Yeah, I think I'm familiar with your work, Lingjie, and I'd be very excited to compare notes on this. So absolutely, I'm familiar with your work.
Cool. Have you done any, to follow up on that question, have you done any comparisons between, the results in their IR and this intermediate range?
So I don't recall off the top of my head what the error estimates are for the MGM. So if I recall correctly, Lingjie, your work focuses primarily on olivine, if I'm not mistaken, right?
Both olivine and pyroxene.
Okay, olivine and pyroxene. Well, I'd be curious to see in particular how your work, handles the variation in calcium composition. So I guess I'm not knowledgeable to comment directly on your work, but certainly interested to learn more.
Nice. Also, have you compared, do you have any lunar sample data to show like the LCC soils to show this trend?
Oh yeah, sure thing. So I don't have any of the soil data with me, but I'll make a couple of comments on soil, on lunar samples in particular. So one is that these samples are the spectrum in the intermediate infrared range generally appear to have only a minor, vary only up to a minor degree as a result of additions of nanophase iron, as we've seen in laboratory studies, and there's some LPSC abstracts I can refer you to. And then as for lunar soil samples, most of the samples that we've looked at so far have mafic mineral abundances of less than 20%. So the Mg number errors are significantly greater than plus or minus 10. However, we have been able to identify olivine and pyroxene bands in those very low mafic mineral abundance samples, and we're looking to make measurements of additional Apollo samples.
Okay, thank you very much.